Let's look at another different topic about the round trip in TCP for the timer. For the timer, we should provide a certain value to the proper timeout. Depending upon the delay time and depending upon the distance or depending upon the time between two sides, sender side, receiver side, and they may be different and there may be various case. That is really random variable, and we need to find out how we can. Question is how to set TCP timeout value longer than RTT round trip time. Then it may work, but depending upon the time value, the performance will be different. If that timer value is too short, then the timer will be expired in premature time. That is called premature timeout. In unnecessary retransmissions, those are happening. If that timer value is too long, it is waiting for too long time, then it is waiting, and to the next procedure, it is going too slowly. That's the slow reaction to segment loss. Then how to estimate round trip time? We can estimate, depending upon the sampled round trip time, measured time from segment transmission until acknowledged receipt. And ignore retransmissions, only the normal transmission case, those are being used for estimation. Sample RTT will vary. We want estimated round trip time smoother, and we need every several recent measurement, not just current sample round trip time. That is called this one, estimated round trip time, and using this equation. Usually this topic is discussed in the graduate course, and this is related to the random variable estimation. This one is just for reference. This one is being used to estimate in real time, because in communication, in the internet, think about internet, the time delay is so variant in real time. Thus, in real time we should estimate. Thus, previous traditional statistical measurement method using the many values together. After that, we are calculating the average value and the standard deviation. That is not acceptable, and that is not usable in our case. We need some real-time scheme for that estimation. This is the way. This one is using some weight to the previous mean value and some weight to this current round trip time, and that is showing the current estimation mean value to apply round trip time. This one is called the exponential weighted moving average, and the influence of past sample increases exponentially fast depending upon that value. Typically value we are using in this TCP, this alpha value will be 0.125, and this one is following like that, and it is asymptotically following that real mean value using that real-time estimation equation, and that is the timer value to use in our timer. In real-time way we can get it. This is a real value for the current one, and that value will be used. Also previous value will be used for the current mean or estimated average value. And we need to consider some standard deviation because there is some variance. This is timeout interval, estimated round trip time plus some safety margin we need. Thus we should estimate also the deviation for that safety margin. Large variation in estimated round trip time that is larger safety margin. Then how we can estimate that the margin, and for that margin we need to estimate deviation. Here we can also estimate that in real time. In this equation we can calculate that. Estimate sample RTT deviation from estimated round trip time. We can use this equation, but instead of alpha here we are using beta. Beta value is 2 times the value of alpha. Alpha was 0.125 in the previous example. Here beta value is 0.25. In TCP we are using this value, and in this equation we can get this deviation of round trip time, and this one is the mean absolute deviation, because we are using this absolute value and mean value also. Here in this way we can calculate in real time. Thus finally our timer value will be set using this timeout interval, that is calculated in this way. Estimate round trip time, that is mean value, and also this deviation 4 times for the safety margin. Then this one is safe timer value for waiting. Let's move to the next topic. This one is about reliable data transfer. Okay. TCP creates a reliable data transfer service on top of IP's unreliable service, as we learned already. And we are using pipelined segments and cumulative acknowledgements, a single retransmission timer. Those are being used for that reliable data transfer. And that retransmission is triggered by timeout events and duplicate acknowledgements. We learn also a little more in detail about this. Let's initially consider simplified TCP sender. Ignore duplicate acknowledgement, ignore flow control, congestion control. That is not TCP, and the simplified one for better understanding initially. TCP sender events. We are considering events because for final state machine design, we need to understand the events, how kinds of events, and what actions depending upon that events. Then we can design final state machine. Data received from application. Then create segment with the sequence number. And sequence number is by-stream number of first data write in segment. And the timer will be started, start timer if not already running. Think of timer as of all these unacknowledged segment. For example, and for reference in advance, TCP is using single timer like a go-back-n protocol. As I mentioned already, TCP is combination of a go-back-n protocol and selective repeat. Among them, timer is being used like a go-back-n protocol. Expired interval, expiration interval, timeout interval, and the timeout. It transmits segment that goes to timeout, and in that case, it starts the timer in this event. And in this event, acknowledged received event, if acknowledged is previous unacknowledged segments, update what is known to be acknowledged. And the start timer if there are still unacknowledged segments, those actions for that event. And that will be simplified, and that will be designed with this final state machine. And the previous slide is melted in this final state machine, for example, timeout. Then retransmit not that acknowledged segment with the smallest sequence number and start timer. Acknowledged received with acknowledged field value y, then that is after this one, then send base will be changed to y, and last cumulative acknowledged byte, and there are this one is, and there are currently not that acknowledged segments, then that start timer will be started again, because we are using single timer in our TCP, like a go-back-n protocol. But we have large buffer instead of the single buffer like go-back-n protocol. That is similar to the selective repeat. This, as I mentioned already, TCP is combination of go-back-n protocol and the selective repeat. Okay, this one is assigning next sequence number after adding up the current data length. This one is a simple interaction explaining about that TCP retransmission scenario. Host A is sending 92, sequence number is 92 and 8 bytes of data. Then the next acknowledgement that will be like this, because that is being expected. Until 99, that is successfully arrived here. The next expected sequence number, that is the first byte of the next expected packet, is 100. And that is being lost. Then we are using timer mechanism. Then timeout will be happening. And after that time out, the same one will be retransmitted. Then that is successfully arrived there. Lost acknowledge scenario that can be recovered without scheme. Also, our TCP is recovering from this premature timeout case. Here, this timer value is premature timer value and too small. And that is timed out in advance like that. Then same one is being retransmitted to this one. Then that is duplication. But still our protocol is working in this way. Even though that is not expected one and previously accepted, and that is acknowledged already, and this one is sending again that acknowledgement again here. Cumulatively last one, because we are using cumulative acknowledgement in our TCP like that. In this error case, also our TCP is working well. This is acknowledgement is lost. Even though that is lost, still this timer is recovering that. After a certain amount of time, our timer is sending. But we are using cumulative acknowledge. Even though this one is acknowledged is lost, next one is acknowledged successfully here. Cumulative acknowledged. Thus, this one is assuming until this sequence number just below this 119. That is acknowledged successfully, and this one is waiting for next one 120. Thus, this one is sending that sequence number 120 packet. TCP acknowledge generation to design final state machine for our real protocol TCP. Those are finalized already. Thus, we are just reviewing. And depending upon that event and action is being used, then we can design final state machine as I mentioned. Then what kind of events are there? And depending upon that each event, we can use this action, and we are integrating all of them together. Then that is the finalized protocol. Event at receiver, arrival in order segment with the expected sequence number, all data up to expected sequence number already acknowledged. Then action is receiver, TCP receiver action is like that. Delayed acknowledge and wait up to 500 milliseconds. This one is waiting for that. For next segment, this one is not sending immediately acknowledgement. It is waiting for this time duration, 500 milliseconds in our TCP case. If no next segment, then send acknowledgement later. And arrival of in order segment with the expected sequence number, one other segment has acknowledged pending. Then immediately this one is send a single cumulative acknowledgement, thus acknowledging both in order segments. In this case, this is the event, another event. Arrival of out of order segment higher than expected sequence number, and the gap is detected, thus missing. And that is not continuous, then immediately send duplicate acknowledgement indicating sequence number of next expected byte. And in another event, arrival of a segment that partially or completely fills gap, then immediately send acknowledgement and provide that segment starts at lower end of gap. In this way, our protocol is working. With this one, we can design TCP final state machine. Here the TCP fast retransmission, that is important concept. Sometimes this one is being used for the exam question in the government officer exam, Korean government officer actually. Timeout period often relatively long. Long delay before resending lost packets sometimes. And detect lost packet segments by a duplicate acknowledgement. Sender often sends many segments back to back. And if a segment is lost, there will likely be many duplicate acknowledgements. This is mainly to improve our performance. If we are waiting for that timeout period, then the sender is actually waiting for that from the receiver. It takes too much time. But if there is some error during the previous transmission, then as soon as possible, immediately we should send the duplicate one, because that is being lost or in error situation. Thus, we should have some other mechanism to decide whether something wrong in the receiver or not. That is the way. If there is any duplicate acknowledgement from the receiver continuously, I received this one in the same way, I received this one, I received until this one, over three times, it is receiving the same acknowledgement. That is called triple duplicate acknowledgement. Then sender is assuming there may be something wrong. The previous transmission was not successful. Thus, immediately the sender is resending to improve our performance. Resend unacknowledged segment with the smallest sequence number. Likely that unacknowledged segment lost, assuming that is lost. And the sender is sending immediately. Thus, it is not waiting for that timeout. Like this. Here, first two, those are sent, but the second one was lost. And this first one is arrived successfully, and the receiver is sent back the acknowledgement. That is expected. New one is 100. Thus, this one is sending acknowledgement 100. Also, next one is not arrived, but another sequential segments or packets arrived there, and there is some missing, like in the go back and protocol, that is discarded. And this one is same acknowledgement is being sent again. That is called triple acknowledgement. Then sender is assuming, oh, there may be something wrong. Thus, it is sending again that packet. It is not acknowledged yet. That is called fast retransmit. After sender receipt of triple duplicate acknowledgement. This is triple duplicate. And including this, 4 times sender received about the same packet. 4 times that is received that acknowledgement. In this lecture, we are learning about connection-oriented transport protocol, that is TCP. And there are many characteristics of that TCP, and among them we are learning in this lecture flow control. And after that, we'll learn about the connection management. We'll look at some animation related to this flow control. Let's look at this supplementary web page. This one is explaining about the interactive animations of the flow control. Let's look at flow control here. Previous one, go back and protocol, and the selective repeat protocol we learned already. And let's look at this flow control animation. Here, let's read this one first. This interactive animation shows the interaction between the sending application, the TCP send buffer, TCP receive buffer, this is host piece receiver, and the receiving application. The receiving application reads chunks of bytes at random times. When the receive buffer becomes full, this is the buffer for that. The TCP receives advertises a receive window of 0. as described in the text. The sender then continues to send segment to 1 byte of data. Okay, let's look at this one. This menu: start button, faster button, slower button, reset button. And the file size we can choose optionally, 4K byte, 8K byte, or 16K byte. Purpose size, 2K byte, this size, or 4K byte, 8K byte. Initially, let's start from the 16K byte of the file size here. And this is the sender's side, and this is receiver. And let's look at these notes. Host consumes data in 2K byte chunks at random times here. When host A receives an acknowledgement due to window 0, A is receiving the acknowledgement due to window 0. That means the buffer is not ready, buffer is full. Host A sends a packet due to 1 byte of the data. Even though that is full, host is sending continuously 1 byte of data to get some information of the receiver's buffer. If that is not being sent, then there is no way to get that information, and it is assumed for simplicity that this 1 byte is not consumed by the receiver. Okay, let's start to this initial file size and the buffer size, 2K byte here. Okay, that will be consumed, and slower, like this, we can control the speed. You can observe this is buffer, and that is being sent here, and also you can pause. And this one is the acknowledgement. That acknowledgement is containing the information about this buffer, receiver buffer, empty space. Now that is fully consumed. There's spare size is 0. That is window size, 0 byte, no more, empty. Thus that information is given to this sender. This is his acknowledgement segment, and until this 4K byte that is being acknowledged, and that means those are successfully received, and the current buffer size is 0. That information is given to the sender. Then sender is not sending, because that is informed that buffer is full. There's no more empty space. This one is not sending data. Instead of that, it is sending just a single byte for continuous transaction to get some information about that receiver's buffer size, that is window size. And sequence number is like that, and let's resume again, and you can see because of that single byte, this information is given back to the sender. Thus this one is notifying this buffer is empty. The sender can send, because this window size is 2K byte. 2K byte is empty now because that is consumed by the application. And the acknowledgement, and this one still the same, and that is expecting sequence number, and that sequence number segment should be sent to the receiver. Okay, let's start again. That is being arrived there to the sender, and the sender is sending 2K byte, and the sequence number initial first one, the sequence number is this one, and that is being sent. Okay, let's look at next step, and you can see that sent data is filling that buffer, and no more empty space here. The window size will be 0. And the next expected sequence number, that is acknowledgement number, that is being changed, and that will be notified to the sender. It is continuing the transmission until this file is being sent completely. Okay, this one is working in that way. This is called flow control. Flow control is controlling the sender's transmission by the sender, not to make this buffer floating. If there is no empty space, then this one is not sending. Just a single byte to get next information for next sending. That is considering the receiver's buffer situation. That is called flow control. That is preventing the flooding of the receiver buffer. We'll be back to this PowerPoint slide. This one is explaining about that TCP flow control, and this one is receiver's protocol stack. This one, and here network layer and transport layer, and this is application layer in terms of layered architecture. And here application may remove data from TCP socket buffers. Now some segment data is being arrived, or packet is being arrived to this receiver, and that will be sent by the sender, and that will be going up in this protocol stack. Here we are considering this one in terms of our flow control. This is slower than TCP receiver is delivering. Sender is sending slower than TCP receiver is delivering. Thus it is not make this floating. The sender is considering that based on receiver's buffer space, based on that information. Okay, flow control. That is receiver controls sender, so sender will not overflow receiver's buffer by transmitting too much or too fast. And a little bit more in detail about this TCP flow control. Receiver advertises free buffer space, as we observed in the previous animation, by including receive window value in TCP header of receiver to sender segment. In the TCP header format, there is one field. This one is receive window, and that field is related to this one. We'll look at that TCP header format again later. Receive buffer size set via socket options. Initial, this one is about the initial buffer size we can set, and that will be the default depending upon our choice. Usually default value is 4K byte. Many operating systems auto adjust this receive buffer size. This is the full receive buffer size. Initial empty buffer size, and this one is dynamically varying depending upon the data, how much that is being consumed, occupying this area space. That is this buffer data, and the other remaining space that is spare space, in other words, free buffer space. That size, that information is receive window. Thus, receive window means free buffer space, that size. The unit is byte. Sender emits amount of unacknowledged. That means packets still in flight. Data to receiver's receive window value. Thus, it cannot overflow the receiver's buffer because of this limitation. Guarantees receiver buffer will not overflow. Okay, let's move to the other topic. This one is about connection management. Still, we are learning about TCP protocol. And the TCP protocol is providing reliable service to be reliable. Even the connection establishment, connection setup, connection close, that should be safe and reliable. That is called connection management. In the UDP, there is no connection management. And in UDP, no flow control. And in the UDP, no reliable data transfer. We'll learn this one. Okay, this one is explain about connection management. Before exchanging data, we need to establish connection. And the sender and the receiver should handshake to establish that connection. And they are agreeing to establish connection, each knowing the other willing to establish connection. And they are agreeing upon connection parameters. Connection parameters are like this: buffer size and the sequence number, initial sequence number. Those are examples of these connection parameters. And let's look at this client side, and this one is server side. And they are trying to establish connection. And this one is explaining about that connection management. Here, application layer. This one is transporter layer, connection state establishment, and the connection variables. Sequence number, client to server or server to client. We need a sequence number for that. And receive buffer, as we learned, for flow control in TCP, we need the receive buffer current receive window, current spare size of the receive buffer. And this one is network layer. As we learned in the chapter 2, client socket can be created in this way with the host number, name, and port number. And in the server side, in the same way, in the transporter layer, connection establishment state, we want to go to this state to send our segments or packet. And we need these connection variables: sequence number from client to servers, from server to client, and initial buffer size as server and client. And with this primitive method, we can create welcome socket. This is connection socket. We can create that is welcome socket. And this one is waiting for that connection request from the client, as we learned in the chapter 2. And before that, let's look at some wrong situation. Here, if we are using two-way handshake, actually we are using three-way handshaking for reliability in TCP. Why we are not using two-way handshake? Because something wrong may happen if we are using this two-way handshaking. This one is explaining about that. In our conversation, that may be simple and we can understand, but in this computer network protocol, that may be very difficult. If we are using two-way handshaking, sometimes there may be something wrong. Request connection, sequence number, choose sequence number, request connection, and establish. After that, accept connection, that will be established. But there may be some error situation if we are using this two-way handshaking. This one is asking about that. Will two-way handshake that is always working in network? Because there may be different situations, variable delays, and there is transmitted messages because of the previous data loss or message loss. Sometimes message will be reordered, and that's different from our human conversation, and the computers cannot see each other, and that is the main difference. Thus, it will be in error situation if we are using this simple two-way handshaking. Okay, this one is one example about this two-way handshaking failure scenario. Here, using this two-way handshake, after request connection, that is established by the server, and that is accepted. Thus, that is established. But later, that connection, that the client may terminate that. But before that, if there is any retransmission request, then even after that client's termination, that will be arrived to the server. Then the server doesn't know that, whether client is terminating that or not. And this server is establishing that connection. There's only this in the server side, that connection is open, not client side. There's no connection here. Thus, that is called half open connection, no client. This is a kind of attacking by the bad guys to make this server in busy state due to half open connection. Connection variables will be consumed. Okay, here, that's the other example. Here, this one is about the connection request. Here, data is sent. Okay, same interaction. And here, this one is requesting the connection. And after that, after this one is sending data, and that is accepted already. And the same data is being retransmitted. And that is being arrived even after that client termination. Then still this one is accepting that data, even though that is accepted already, because server doesn't know that. Then this one is in bad and error situation. Thus, we are using three-way handshaking instead of two-way handshaking because of the previous problem. Here, client side, I changed this one to the closed state. Original PPT was listen, that is wrong. That may be used here. To understand better, I intentionally put this closed state here. Before server is booting up, that will be closed here, and after that, that will be active. Then that will be go into this listen state. And to match to the final state machine, I intentionally changed this one, because this one is correct one. Closed, seen sent, establish. This server state is state. Listen, seen received, and establishment. Let's look at in advance this one. Three handshaking final state machine. Closed, this one is server. Listen, server is listening, and seen received, and establishment state. This is client side. closed and the SYN sent established. And these states, those will be matched to this one. This one in the client side, this one is server side. Thus I changed this one. Instead of listen, that should be closed. Initially, client is closed state, and after that, this client wants to send some request to the server to do connection establishment. Thus choose initial sequence number and X, that is X, and that is random number. Initially that is being chosen, and after that the others will be following depending upon that initial value, sequence number. Send TCP SYN message. This is a SYN. When we are starting, then this SYN flag, that is called the SYN segment or SYN message. The SYN bit, as we learned already in the segment structure, there is flags, and the SYN bit, this flag will be 1. That means this one is starting. And the sequence number, this is initial random number that is being used here. And also this one is choosing initial sequence number randomly by the server, and that is Y. And send TCP SYN acknowledge. This is a SYN bit and SYN segment, and that will be acknowledged to this SYN bit and acknowledge. The SYN bit and acknowledgement bit, those bits are changed to 1. And you can observe this one with the Wireshark in the Wireshark lab. And this one is being sent. The SYN acknowledgement segment will be sent. And like this, SYN bit 1, acknowledgement bit 1. This is called the SYN acknowledge. And here, that is acknowledged. And the sequence number is being sent here. And this one is receiving SYN acknowledge, that segment, and indicates server is live, and send acknowledgement. This one is acknowledging again for that SYN acknowledge. Thus, this one is a three-way handshaking. This segment may contain client to server data. This may contain here, if that is connection establishment, and this one is three-way handshaking example. This one is receiving acknowledgement sent from the client. After that, this one is moving into this establishment state. In the previous state, in the server side, listen state, because this one is in the listen state, this one can accept client's request, and after there is some event requested by the server, that will be the event, and this one is the action for that. Event is request SYN bit 1 and some request from the client. After that, this one is SYN received. This SYN bit is received. That is the event. After that, this one is the action, sending this one and the others. That is the action. And now, in terms of the event and the state, this one is in the SYN received state after receiving that event. And also, after receiving another next acknowledgement, confirmed, that is confirmed, thus it is moving into this new state, establishment state. Our purpose is to be in this establishment state reliably. This TCP three-way handshaking is providing this reliable connection establishment. Let's look at client side. First, it was closed state. Later, it is doing some action. Then, after that, this one is going into this state, SYN sent, because this one is sent, that SYN segment, to the server. And this one is waiting for the acknowledgement, SYN acknowledgement. After that, after receiving that That is event. After that, it is moving to this state. It is changing the state to this establishment state. That's it. After this connection establishment, we can send and receive the next real data. After this connection, this HTML file and others can be sent and can be received in this establishment state. We are now focusing on that connection establishment. In terms of the final state machine, as I explained already, this one is the server side, this one is client side. In the server side, initially it was closed, and this one is booting up, and the server program is running. Then it is moving to this listen state. Let's look at this three-way handshake final state machine for TCP. As we observed already in the previous slide, that slide, I also showed this state. And this one is the final state machine and for the server side. And this one is the final state machine for client. In the server side, let's look at first. Server, the state is initially closed, and after booting up and the server program is running, then this welcome socket is waiting for the request from the client, and this welcome socket that will be created in this way, and it is waiting for that. And this one is listen state, and from this listen state, if there is any SYN segment from the client, then it is moving to the SYN received state. And this one is the action. After receiving that SYN segment, sequence number, acknowledgement number, and create new socket for communication back to client, and that packet will be sent to the client, and then client is actually this one requested with this SYN segment, and the SYN sent the state. This one is waiting for that, and if this one is receiving that SYN acknowledgement from here, and acknowledgement will be sent to the server, and this one is receiving in this SYN received state, because this one is sent and received, and here in this state, this one is waiting for that acknowledgement sent from the client. After that, they are in this establishment state. After that, they can send and receive the real data in this TCP. We learned about the connection establishment. When we are trying to finish, we need to consider how to close that connection. And this one is about the closing a connection. And also this one is important for reliable communication, reliable service, because even that closing of that connection is important. Reliably, that connection should be closed in the TCP. Client server each close their side of connection. Send the TCP segment with the pin bit equal 1. Here we are using pin bit to finish, to close. Respond to receive the pin bit with acknowledgement. On receiving pin, acknowledgement can be combined with one pin. Okay, let's look at this one first. Simultaneous pin exchanges can be handled. And this one is the interaction between client and the server, like this, like this, like this. Okay, this one is not showing final state machine, and this one is explaining only with this interaction between client and the server. And this one is the state for that. 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 And this one is the state This is server side, server state. And client state, here establishment state. Closing can be possible in the establishment state because we are trying to close during that establishment. First, client socket.close. We can use this program to close. Then pin bit is being used, and that pin segment will be sent to the server. Then server is moving into this close wait state right after receiving that pin bit, depending upon that event. And it is doing some action. That action is sending this acknowledge bit 1 and acknowledgement number, sending this acknowledgement segment to the client. Here in the client, after sending that pin bit, this one is in the pin wait number 1 state, can no longer send but can receive data. And after receiving some acknowledgement from the server, this one is moving into this pin wait 2 state, and here wait for server close. After that, sending some data that is possible. If there is some remaining data to send, then after completion of that sending, server can close. Thus, this one can still send data like this. After that, this one is sending pin bit. This is first time by the server to send this pin bit. Originally, this pin bit from the client that was arrived here. After finishing other data transfer, if there is any remaining data to send, then after completion of that, this one server is sending pin segment to the client. Then this one is in the timed wait state, and after a certain amount of time, usually 30 seconds, 1 minute or 2 minutes, that will be closed. Here can no longer send data and closed. This one is last acknowledgement. This one is about that. This one. After that, that is closed. Okay, that's it.